Chapter 7, System of Particles and Rotational Motion. Introduction. In the earlier chapters, we primarily considered motion of a single particle. A particle is ideally represented as a point mass having no size. We applied the results of our study even to motion of bodies of finite size, assuming that motion of such bodies can be described in terms of motion of a particle. Any real body which we can encounter in our daily lives has a finite size. In dealing with the motion of an extended body, often the idealized model of a particle is inadequate. In this chapter, we shall try to go beyond this inadequacy. We shall attempt to build an understanding of motion of extended bodies. An extended body, in the first place, is a system of particles. We shall begin with the consideration of motion of a system as a whole. The center of mass of a system of particles will be a key concept here. We shall discuss the motion of a center of mass of a system and the usefulness of this concept in understanding motion of extended bodies. A large class of problems with extended bodies can be solved by considering them to be rigid bodies. Ideally, a rigid body is a body with perfectly definite and unchanging shape. The distance between all pairs of particles of such a body does not change. It is evident from this definition of a rigid body that no real body is truly rigid, since real bodies deform under the influence of forces, but in many situations the deformations are negligible. In number of situations involving bodies such as wheels, tops, steel, beams, molecules and planets, on the other hand, we can ignore that they wrap, twist out of shape, bend or vibrate. What kind of motion can a rigid body have? Let's consider a rectangular sliding block downward an inclined plane without a sideways movement. The block is taken as a rigid body and its motion down the plane is such that the particles of the body are moving together. The rigid body here is in pure translational motion. In pure translational motion at any instance of time, all particles have the same velocity. Consider now the rolling motion of a solid, metallic or wooden cylinder down the same inclined plane. The rigid body in this problem, namely the cylinder, shifts from top to bottom of the inclined plane and thus seems to have translational motion. The best common way to constrain a rigid body so that it does not have translational motion is to fix it along a straight line. The only possible motion of a rigid body is a rotational motion, and the line or fixed axis about which the body is rotating is the axis of rotation. If you look around, you will come across many examples of rotation about the axis: a ceiling fan, a potter's wheel, a giant wheel in a fair, a merry-go-round, and so on. Every particle of a body moves in a circle which lies in a plane perpendicular to the axis and has its center on the axis. In some examples of rotation, however, the axis may not be fixed. A prominent example of the kind of rotation is a top spinning in its place. We assume that the top does not slip from place to place and does not have translational motion. We know that the experience that the axis of such a spinning top moves with the ground. This movement of the axis of the top around the vertical is termed as precession. Note that the point of contact of the top with the ground is fixed, and the axis of rotation of the top at any instance passes through the point of contact. Another simple example of this kind of rotation is oscillating table or pedestal fan. While the fan rotates about its axis and moves sideways, this point is fixed. Thus, in more general cases of rotation, such as the rotation of a top or a pedestal fan, one point is fixed. In this case, the axis is not fixed. In our study, however, we mostly deal with simpler and specific cases of rotation. The rolling motion of a cylinder down an inclined plane is a combination of rotation about a fixed axis of translation. Thus, something in the case of rolling motion, which we referred to earlier, is rotational motion. We now recapitulate the most important observation of the present section. The motion of a rigid body which is not pivoted or fixed in some way is either pure translational or combination and rotation. The rotation may be about any axis that is fixed or moving. Center of mass. We shall first see what the center of mass of a system of particles is and then discuss the significance. Motion of a center of mass. Equipped with definition of center of mass, we now are in a position to discuss the physical importance of a system of n particles. Mr is equal to summation of mi into ri is equal to m1 r1 plus m2 r2 m3 r3 up to mn rn. Differentiating on both the sides with respect to time, we get m d of r dr by dt is equal to m1 dr1 by dt plus m2 dr2 by dt. mv is equal to m1 v1 plus m2 v2 plus up to mn vn. And now the Newton's second law, the force acting on the first particle is given by F1 is equal to ma, and the force acting on the second particle is given by F2 is equal to m2. The center of mass of a system of particles moves as if all the mass of the system was concentrated to the center of mass and an external force was applied at that point. Notice we determine motion of the center of mass with no knowledge of internal forces of particles required. So, linear momentum of a system of particles. Let us recall that linear momentum of particles is defined as P is equal to mv, and let us recall the second law written in symbolic form for a single particle is, where F is the force of a particle. Let us consider the system of n particles with mass m1 up to mn respectively and velocities v1 up to vn. For a system of n particles, the linear momentum of system is defined to be vector sum of all the individual particles. P is equal to P1 plus P2 up to Pn, m1 v1 plus m2 v2 up to mn vn. Total momentum of a system is equal to the product of the total mass of the system and the velocity of the center of mass. The statement of Newton's second law of motion is extended to a system of particles. Angular acceleration. You may have noticed that we are developing the study of rotational motion along with the lines of the study of translational motion, which we are already familiar with. Analogous to the kinetic variables of linear displacement s and velocity v in translational motion, we have an angular displacement and angular velocity in the rotational motion concept. It is then natural to define in rotational motion the concept of acceleration in analogy with linear acceleration. Torque and angular momentum. In this section, we shall acquaint ourselves with two physical quantities, torque and angular momentum, which we define as vector products of two vector quantities. These we shall see on a these we shall see are especially important in the discussion of motion. Moment of force or torque. We've learned that motion of a rigid body is in general a combination of rotation and translation. If the body is fixed at a point or along a line, it is called rotational motion, and we know that the force needed to change the translational state of a body, that is to produce linear acceleration. We may ask this that the analog for force in this case of rotational motion is still to be defined. To look into the question in a concrete situation, let us take an example of opening or closing a door. A door is a rigid body which we can rotate about a fixed axis passing through the hinges. What makes the door rotate? It is clear that unless a force is applied, the door does not rotate, but a force does not do its job. A force applied to the hinges line does not produce any motion, any rotation at all, whereas a force given of magnitude applied at right angles is at its outer edge is most effective in producing rotational motion. Rotational analog of force in linear motion is momentum of force, and we shall study the words of moment of force and torque interchangeably. Angular momentum of a particle. Just as the moment of force is rotational, analog of force is in linear motion. The quantity of angular momentum is of rotational motion. We shall first define angular momentum as a single particle and look at its usefulness in the context of a single particle motion. We shall then extend the definition of angular momentum to the systems. Consider a particle of mass m and linear momentum p1 at position r relative to its origin. L is equal to r into p. The magnitude of angular momentum is L is equal to rp sine theta, where L is the momentum and r is the radius, or the relative position of the origin. Torque of momentum for a physical system. To get the total angular momentum of a system of particles about a given point, we need to add vectorially the angular momentum of the individual particles. Let L1 is equal to L1 plus L2 plus L3 up to Ln. An angular momentum of the nth particle is given by Li is equal to Ri into Rp. Equilibrium of a rigid body. We are now going to concentrate on the motion of rigid bodies rather than on motion of general systems of particles. We shall recapitulate what effect of external forces have on rigid bodies, and henceforth we shall omit the adjective of external, because unless stated otherwise, we shall deal with only external forces and torque. The forces change the translational state of motion of a rigid body. A rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changed with time. Acceleration or angular acceleration. The total force is a vector sum of the forces of the rigid body, that is 0. The total torque, the vector sum of the torques of a rigid body, is 0. The condition of equilibrium of a rigid body may be compared with those of a particle, which are considered in earlier chapters. Since consideration of rotational motion does not apply to a particle, only the conditions of translational equilibrium can apply to a particle. Thus, the equilibrium of a particle is said to be zero, since all these forces act on single particles. A body may be in partial equilibrium. It may be in translational equilibrium and not in rotational equilibrium, or it may be in rotational equilibrium and not in translational equilibrium. The force is reversed, and thus we have the same rod with two forces in equal magnitude but acting in the opposite directions. A pair of forces of equal magnitude but acting in the opposite directions are is called a couple or a torque. We now open the lid of a bottle by turning it. Our fingers are applying a couple to the lid. Another example is a compass needle in the Earth's magnetic field. The Earth's magnetic field exerts another equal force on the north and south fields. The force on the north pole is towards the north, and that towards the south is towards the south. Thus, there is a couple acting on the needle due to the Earth's magnetic field. Center of gravity. But many of you have the experience of balancing your notebook at the tip of your finger. Illustrate a similar experiment where you can easily perform. Take an irregular shaped cardboard having mass m and a narrow tipped object like a pencil. Try to balance it on the tip of the pencil and observe through the experiment. Moment of inertia. We've already mentioned that we are developing the study of rotational motion parallel to the study of translational motion. With what is the analog of mass in rotational motion? We shall attempt to answer this question in the present section. To keep the discussion simple, we shall consider the rotation of a fixed axis. Let us try to keep an expression for kinetic energy of a rotating body. Dynamics of rotational motion about a fixed axis. We've already compared kinematics to the two motions. Also, we know that rotational motion and torque play the same role as mass and force respectively. Given this, we should be able to guess that the other analogues indicated in this table are, for example, we know that in linear motion, work done is f of dx. But before we log in, we note a simplification that arises in this case of rotational motion about a fixed axis. Work done by torque. Conservation of angular momentum. We now are in a position to revisit the principles of conservation of angular momentum in context of the above fixed axis. L is equal to I omega is equal to constant. This is then required to form for a fixed axis of rotation, which expresses a general law of conservation of angular momentum of a system. A circus acrobat and a diver takes advantage of the principle. Also, skaters and classical Indian writers and dancers performing a spinning or tip-top on the toes of the foot can display a mastery over the principle of angular momentum. Rolling motion. One of the most common motions observed in daily life is a rolling motion. All wheels used in transportation have rolling motion. Specificness, we shall begin with case of disk, but a result will apply to any rolling body. We will assume that the disk rolls without slipping. This means that at any instance of time, the bottom of the disk, which is in contact with the surface, is at rest. Summary: ideally a good body is ideally a rigid body is one for which the distances between different particles of the body do not change, even though there are forces on them. A rigid body fixed at a point or along a line can have rotational motion. A rigid body not fixed in some way can have either pure translational motion or a combination. The vector cross product of two vectors A and B is a vector written by A cross B, and the magnitude of this vector is AB sine theta. This direction is given by a right-handed screw, and the linear velocity of a particle of rigid body rotating about the axis is given by V is equal to omega cross r, and the velocity of the center of mass of a particle is given by V is equal to P by M. The angular momentum of a system of n particles about the origin L is equal to Ri into Pi, and torque is equal to summation Ri into Fi. The theorem of parallel axis Iz dash is equal to Iz plus Ma allows us to determine the moment of inertia of a body about the axis as the sum of the moment of inertia of the body about the parallel axis through its center is the mass of the product, and the square of the perpendicular distance between these two axes. Rotation about a fixed axis is directly analogous to linear motion in respect to kinematics and dynamics. For rolling motion without slipping, Vmn is equal to r omega, where v omega is the velocity of translation, and r is the radius, and m is the mass of the body.